Hi, in this video I want to talk about what is called the common ion effect. It is a type of KSP or solubility product calculation. But in this case, instead of having a situation like if I have lead chloride going to lead ion plus 2 chloride ions, these are typically 0, but in a common ion problem, what we're doing is providing another source of an ion that is effectively in common with the insoluble salt. So we could add some lead nitrate. So instead of being 0, that could have a new value. Or I could add some sodium chloride. So again, instead of being 0, I could have a value there. Now, you want to be really careful because that common ion, that concentration will go into the initial row of ice, the I row. And be careful because you're going to have an insoluble salt and you're going to be provided information of a soluble salt, and there's going to be a temptation to add the two substances together. But don't give in to that temptation. Let's do it, and I think it'll help you understand what I mean a little bit more detail. So I've got lead chloride, so PbCl2 solid. It's going to dissociate to make lead ion aqueous plus chloride ion aqueous. Okay? But this time, instead of being just pure lead chloride in water, I'm adding lead chloride to a solution of calcium chloride. So let's identify our substances. Here I have an insoluble salt. Sorry, missed the S there. The lead 2 chloride is considered an insoluble or slightly soluble salt. And the calcium chloride is a soluble salt. So I've identified my substances. We don't have any dilutions, but there is a stoichiometry here. A variety of ways to do that stoichiometry. I think the simplest way is to do ions within. So I have 0.5 moles per 1 liter of calcium chloride, and the ion that's in common is the chloride ion. So I'm going to multiply that by the mole ratio. There's 2 moles of chloride dissociated for every 1 mole of calcium chloride that is in solution. And so I have a chloride solution of 1.1 molar. None of my lead ion, there's no other source of lead besides the soluble salt. We're not interested in solids there. So I have plus S plus 2S. Add the ion C, I get S and 1.1 plus 2S. Now, we are going to neglect this 2S, but let me show you a trick to know how you know whether we can neglect it or not. So, if you take the value in front of an added or subtracted unknown, if this 1.1 is greater than 100 times K, then it's okay to neglect. So if I take 100 times K, I want to ask myself the question, is it greater than 100 times 1.7 times 10 to the minus fifth? And indeed it is. If that's the case, it's okay to neglect the added or subtracted unknown. And what that does is it tremendously simplifies our math. So we're going to neglect that. So now KSP, which is lead ion, times chloride ion, almost forgot to balance that, squared, okay? And I'll get S times 1.1 is equal to 1.7 times 10 to the minus fifth. And if I solve for my solubility, I get 1.4 times 10 to the minus fifth molar. Okay? Now, just for comparison's sake, I want to show you what the solubility in pure water would have been. If we'd done that calculation, our solubility without the common ion was 1.6 times 10 to the minus 2 molar. So our take-home lesson is this: the addition of a common ion decreases our solubility. It forces the reaction to be pushed more in the reactant side than the product side. So that's the take home there. Okay. Now, the other question that was asked, just to kind of keep reviewing a few concepts, is this is my solubility, 1.4 times 10 to the minus fifth moles per liter. The question asked for the solubility in grams per liter. So I have to eliminate moles and go to mass. Moles to mass use molar mass. And I get 4.0 times 10 to the minus 3. Don't forget your units. Watch your sig figs. 2 sig figs. And that would be my solubility in grams per liter. Okay, I think that's a little tricky, so I want to do another one. You can always rewind that one or slow me down. I know people who speed me up. I can't imagine that because I feel like I talk so fast as it is, but I do. I know people who watch me on time and a half. Don't tell Jonathan Bergman, but I watched his whole class. I did my whole flip training certification on time and a half. So I've got silver chromate here, and that's a solid. I didn't leave myself much room here. So I'm going to put those states above just as a reminder to ourselves so we don't mess up. I'd say the biggest, not biggest, yet another mistake I see is people including those solids in the KSP. KSP does not include solids. So my cation is Ag+, and I have 2 of them. My anion is chromate. So KSP is silver ion squared times chromate ion. And you notice my solid does not show up. That's why some students like to put the number 1 under their KSPs. It's just a continual reminder to themselves. Don't include that stinking solid. Okay? I'm not going to worry about the solid. We've identified, let's do that. So silver chromate's an insoluble solid, but we've also added potassium chromate. Potassium chromate is a soluble salt. And soluble salts mean we have to do some level of a stoichiometry. There is no dilution. We did not add volume to volume. So in this case, honestly, this is all I would expect to see from my students, is that my molarity of potassium chromate is the same as my molarity of my chromate because it's a 1-to-1 mole ratio, and that's equal to 0.005. Okay, and so I don't have another source of silver. This is 0.005 plus 2s plus s, 2s, 0.005 plus s. Now, if you take 100 times k, I have to the minus 10th power there. 0.05 is much larger than that. So we're going to neglect that addition or subtraction of an unknown. And now when we plug in, 1.1 times 10 to the minus 12th is equal to 2s, careful, 2s squared, don't forget to square that 2, times 0.005. And I get from my solubility that it's equal to 7.4 times 10 to the minus 6 molar. Okay? Now, I'm not done. Make sure you read your question. What did the question ask us? The question didn't ask us for the solubility. It says to calculate the solubility, excuse me, that was the first step. But then it said determine the concentrations of all ions present in the solution. So let me get myself a little bit of room here. I want to keep my solubility value there. My silver ion is equal to 2 times S, so it's 2 times 7.4 times 10 to the minus 6. So my silver ion is 1.5 times 10 to the minus 5th. And molar. And this is 0.005 plus S, and that's pretty much approximately equal to 0.005. So do that subtraction and round to sig figs, and you're going to get 0.005 molar. Okay, so those are common ion problems. Biggest challenges. Don't try to add, I'll tell you, biggest challenge, don't try to say, oh, I've got potassium chromate, and I put it into the solution with silver chromate, and I'm going to have a reaction. Well, there is no reaction. Ionic, it just doesn't react. You'd have a double replacement with the same products as reactants. So that's not what you want to do. Just because two substances are in a beaker together doesn't mean they chemically react together. And then the other one is watch that denominator on a KSP. Thanks for joining me.